Hello, beta. Good evening.
Good evening, sir.
Good evening, beta. Good evening. So, how are we today?
Perfect, sir. All going well.
Okay, great. Okay, so beta, yesterday we were doing the GPS, and the only thing which was remaining was the differential GPS. So today we are first going to cover up the DGPS, And then after DGPS, we are moving on to the remaining equipment. Maybe we can pick up AIS, Automatic Identification System. That's a similar system. And then we can go to voice data recorder and Banvas, those equipment. So ready, beta? Shall we go ahead?
Yes, sir.
Okay, all right. Let me put up the presentation, beta. So first we start with the DGPS, the differential GPS. Now moving further to a subsidiary system, a add-on system, which makes the GPS position fixing more accurate. Now this is known as differential GPS, or in short DGPS. A differential global positioning system, or DGPS, is an enhancement to the GPS system which provides us with improved positioning accuracy. Now, in the DGPS system, a DGPS reference station is situated at a fixed location and it receives the GPS data from the satellites. A computer at the fixed location calculates the pseudo range from the GPS satellites and then compares it with the actual range or the known ranges for that precise geographic location. So one is the calculated range, which is basis the data which is fed in, and second is the actual range which is received from the satellite. It then computes a range error by comparing these two ranges to figure out which is then broadcast over the MF frequency band to all the mobile stations to improve the positional accuracy. The differential GPS can give us an accuracy of about 1 to 10 meters based on the CA code using standard positioning system. So you can see we can receive or we can generate the accuracies related to the P code or the precise positioning system using this DGPS with only the CA code. So with this, we close out the global positioning system. Thank Okay, one more item, beta, one more thing. Let me tell you the two ways in which the corrections can be provided. Once the error is calculated by the DGPS station, now this error can be passed on or the corrections may be given to the receivers in one of the styles. One could be the position correction in terms of latitude, longitude, and altitude. A correction is sent which is to be applied to the latitude, to the longitude, and to the altitude of every user. The second way could be the correction to be applied to the pseudo ranges of each satellite. The specially equipped GPS receivers receive the error information and apply the necessary correction to their own fixes. These corrections are valid only within a specified area which is close to the DGPS ground station. On-board receivers may be programmed to auto-track DGPS stations, receive the corrections from them whenever available, and apply the same to their own fixes. There is usually an indication on the display whenever a DGPS transmission is available, and through that indication you can find out that the GPS is being enhanced using the DGPS technique. So any doubts in the DGPS system, beta? Okay, beta, great. So closing down the presentation now. Now, beta, next I'm taking you to the AIS, the Automatic Identification System. So this AIS is also dependent upon the GPS system. It cannot work without a GPS. So we will see what is this AIS system, what is the principle on which it works. The principle is known as SOTDMA. So we will see what is this SOTDMA principle, then what is the information which is transmitted and received in the AIS, and then the some techniques like pseudo AIS which are coming into existence now, being used in some of the places. So that is what we are going to see. So let me put up the presentation. In this presentation, we are going to discuss and learn about the AIS, Automatic Identification System. Now, before we go into the working and operation of the system, it is always a very good practice to go into the history of the equipment. Why was this equipment required? Now, some of the important reasons which justify the need for automatic identification system were: number one, lack of positive identification was one very troublesome weak link in the chain of communication and identification before the AIS. We had the radar available to us to detect the targets close to the ship, but the radar did not identify the target positively. Radar could give us the range and bearing of the target, but we were not able to positively identify the target. AIS has taken care of this problem. With AIS, the target is automatically identified. Other limitations which were there in radar as well as ARPA also necessitated the coming in of the AIS. Now, the radar as well as the ARPA equipment are dependent upon the state of weather. With the weather becoming bad, the effectiveness, the performance of radar as well as ARPA both go down. The efficiency and performance of the radar equipment also keeps on changing and needs to be monitored regularly and carefully. The radar as well as ARPA have problems like losing targets. In case a target is altering its course, there is a tendency that the target may be lost. There is a problem of swapping of target. When two targets being tracked by ARPA come close to each other, sometimes the targets jump, the targets are swapped, and for some amount of time, the information on the ARPA is not displayed correctly. Also, as the performance standards require, there is a 3-minute time limit relaxation which is given for ARPA. ARPA can take up to 3 minutes of time to display the target data. And with radar and ARPA, there is a issue of blind and shadow sector. With the funnel, with the mast, with the cranes, it is possible that a certain part could be a blind sector or a shadow sector for the radar, and that could hamper the identification and information about the targets in our vicinity. Now, AIS takes care of all these limitations. Another very important reason why the AIS came in was the security concerns. we had the Twin Tower attacks, and with those attacks, we had the arrival of ISPS regulations. And these ISPS regulations made the AIS as a mandatory equipment. It emphasized that there is a need for automatic and positive identification of ships in the vicinity, and that was what led to the bringing in of AIS into the maritime domain. Let's now go into the principle on which the AIS system works. The principle on which AIS works is known as SOTDMA, and it is very similar to the system which we use in our mobile phones also. The system which is used in mobile phones is the CDMA system. It is one of the systems which is used for mobile communications. CDMA stands for Code Division Multiple Access. The system on which the AIS works is SOTDMA, and it stands for Self-Organizing Time Division Multiple Access. Now, as is clear from the name itself, that this system is self-organizing. That means it does not require a master or a controller as is required in the mobile systems. Our system, the AIS system, does not require any operator, controller, or a master. The second term is time division. This system is based on dividing the time into multiple slots. So these slots are acting like turns for all the ships to transmit their data. So that is why the term time division. This system works on dividing the time into small slots of time. And the last term in the name is multiple access. That means it allows multiple users to access the system at the same time, and information can be passed on or communicated between multiple systems within a short duration of time. Now, as we discussed just now, the SOTDMA is fully automatic, and it works without any involvement from the duty officer, or it works without any human intervention. It does not suffer from problems of interference. There is no interference between the stations, as the time slots are well defined, and every station has a different time slot. And also the system is able to and is having the capability of resolving any conflicts if they arise on its own. Thus it is called as self-organizing. It divides a unit of 1 minute of time into a number of slots. The minimum number of slots as per the IMO standards are 2000 slots in a minute. So these are slots or time schedules which allow different stations to transmit their information, and every station is able to access the information of everyone else in that particular region in a very short span of time. Now, when we are dividing the time into slots, we are basically talking of the resolution of milliseconds. So when we have this much of time accuracy, normal clocks are not going to work for this particular system. So we need the accurate time signals from GPS. The GPS time is very, very accurate. The GPS positioning is dependent upon the clocks which are there in the GPS system. So these highly accurate time signals from the GPS are utilized for setting up this SOTDMA system of the AIS. So from here it becomes clear to us that the AIS is dependent on the GPS for its operation. If the GPS fails, the AIS system will not be able to work at all. Now, for this purpose, the AIS equipment which we have on board is either given a feed from the ship's GPS, or if it is a high-tech equipment, it could have its own positioning capabilities, or it could have its own GPS fitted inside the unit. Now, this diagram which you see basically summarizes the entire operation which we just now discussed into one picture. Let us understand this diagram. Let's assume that there is a particular area, and in that particular area we have two ships. So ship A, the red ship which you see here, and ship B, the green color ship which is there. Let's say it's a anchorage area, and there is no other station, the AIS station in VHF range. Let's say a third ship enters in that area, that is ship C. It has entered into this area. There is no other ship anywhere. Now the AIS of ship A and ship B was already working. Ship C has entered in this area just now. So how does the system work? The AIS present on ship C, the blue color ship, first it goes into the reception mode. It tries to receive the data transmitted by the ships which are already present in that area. So ship C is going to wait for the transmission from ship A as well as ship B. Now this bar which you see on top, it basically represents the time slots made with the help of GPS time signals, which is being followed by ship A and ship B. So you see each time slot represents 26.6 milliseconds. So in this particular time slot, the transmission is made by the red ship, ship A, in this particular slot. Now the AIS system is such that whenever any station transmits the information, at the same time, it books a slot in the future. So you see this particular slot is booked by the red ship for its next transmission. So you can see it here also. The AIS of ship A sends the position message in one time slot. At the same time, it reserves another time slot for the next position message. So ship C, the blue color ship which has just entered the area, receives this information. Now after some time, the ship B transmit its data at this particular slot. So in this green slot, it transmits its own data, and then you see there is a future slot which is booked for its next transmission. Now when both ships have done completed their transmission, the ship C has their data, so the navigator who is there on ship C will be able to see the data for both these ships, and at the same time ship C is also aware of the future time slots where these two stations are going to make their next transmission. So ship C is immediately able to find out the vacant slots, and in one of these vacant slots, now the AIS of ship C fires up and transmit its own data. So both these ships, ship A and ship B, receive the data of the new entry vessel, that is the blue color ship C. And when this transmission is made by ship C, at the same time it reserves a slot in the future where it is going to make its next transmission. So the same procedure is repeated by all other AIS equipped ships, and they keep on finding these empty slots. They keep on transmitting their data, booking one slot into the future and letting all other stations know which slots are vacant where the data can be transmitted. So I told you there are minimum 2000 slots in a minute. So in a minute, minimum 2000 stations would be able to transmit the data. Now at this particular time, as far as navigation is concerned, I hardly see any areas where you will have 2000 ships in the VHF range. It is possible if the AIS is fitted over each and every single boat or something like that. But even then, the system is quite equipped to handle this much of traffic. So up to 2000 stations per minute is not a problem at all. Even if the number of stations try to increase, the AIS has further capabilities to handle that extra pressure also. So this is the SOTDMA principle. Now, something related to the operation of AIS on board. AIS in the normal circumstances should always be in operation on board. Now, in case the master believes that the operation of AIS might compromise the safety or security of the ship, it may be switched off. It is within the authority of the master. Now, this might be the case in sea areas where pirates and armed robbers are known to operate. Whenever taking actions of this kind, it should be recorded in the ship's logbook together with the reason why it is being done. AIS should be restarted as soon as the danger is over. Now, in ports, the AIS operation should be in accordance with the port requirements. So in some of the ports, they are very specific about AIS. In fact, if your AIS data is not properly updated, they may put fines on the ships. Heavy fines may be levied on the ship in case of misleading AIS information. Secondly, every port, every terminal will have its own requirement. Some of them tell you to put the AIS into a low power mode, whereas some of the terminals or port may tell you to altogether switch off the AIS. Now let's come to an important aspect of what all information is transmitted over the AIS system. Now this information is divided into three data packets. The first one is static information. As is clear from the name, the static information is something which is static and does not change. The second data packet is the dynamic information. As again obvious from the name, this is the information which keeps on changing with time or from ship to ship or the third data packet which we have is the voyage related information. So this is the data related to that particular voyage which the ship is undertaking. So let's see now under all these three heads what information is transmitted and received by the AIS. So we have the under static information, we have the MMSI number, the IMO number wherever available, the call sign and name of the ship, length and beam of the vessel, type of ship, and location of the position fixing antenna on the ship, aft of bow, and port or starboard of the center line of the ship. So as you can see, all this information is static or fixed in nature. So it comes under static information. Now coming to dynamic information which keeps on changing, we have the ship's position, the time, course over ground, speed over ground, the heading of the ship, navigational status, for example, whether the ship is at anchor, ship is underway, aground, etc. This is input manually, and the rate of turn wherever it is available. So if a rate of turn indicator is connected, yes, it should be transmitted and received. The navigational status is also important from the point of view of transmission, because the frequency of transmission means after how much time a new data packet should be transmitted by a particular station. It also depends upon the navigational status of the ship. A ship which is at anchor will have most of its data which is stable, not changing. So the frequency which is required is much lesser as compared to a ship which is moving. So a moving ship will have to update or transmit its data at a frequent interval at a higher frequency. Let's come to the voyage related information now. The ship's draft, the type of cargo, the destination and ETA. Now this could be commercially sensitive information, especially in case of containers, ships like container ship or passenger vessels. So it has been left to the master's discretion whether he wants to display or transmit or broadcast that information to other ships or not. And the route plan or the waypoints, which is again left optional. This could also be a commercially sensitive data. Now, after these three information packets, there is an option that we can send and receive safety related messages. So free format, short text messages can be sent and received as and when required. So the capacity is, if I remember correctly, it's 121 characters. So these messages should be safety related and they can be transmitted to a particular station or they can be broadcast to all the stations in the range. Okay, now we come to a very important aspect of the system. That is the reporting interval for AIS transmissions. What are these reporting intervals? I discussed with you a little while before that the frequency with which the messages are sent, it basically depends upon the navigational status of the ship. For a ship which is at berth or which is at anchor, the data is not changing at a very fast pace. The dynamic data is also stable. It is not changing. That is the position, course, speed, everything. They are also not changing. The static data remains the same. The voyage related data is also not changing. So we require a much lesser frequency. The messages need not be transmitted at a very fast rate because the data is not changing. So if you compare it with a ship which is moving fast, let's say also altering its course, then the data needs to be updated fast. The frequency has to be higher because when you watch that ship on your AIS, and if the frequency is less, the frequency is not fast, in the case of a fast moving ship which is also altering course, it is possible that the AIS data may be outdated. The ship actually may be at some other location, at some other heading, at some other course, doing some other course and speed, whereas your AIS may give you the data which is already outdated. So that could lead to a near miss or a dangerous scenario if the data which you are getting from the AIS is not up to date. So that is why a reporting interval or a frequency has been set down depending upon the navigational status of the ship. So let's see these frequencies. A ship which is at anchor or moored and not moving faster than 3 knots has to send the AIS message every 3 minutes. Ship at anchor or moored and is moving faster than 3 knots, that could be a case when the ship is dragging anchor, or let's say you are moored to the buoys and the buoy moorings are shifting or they are just dragging over the ground, some scenario kind like that. So in that case, the reporting interval is 10 seconds. Ship which is proceeding en route with 0 to 14 knots, the frequency is 10 seconds. The ship proceeding with 0 to 14 knots and changing course, it is 3.3 seconds. Ship 14 to 23 knots, the frequency is every 6 seconds. 14 to 23 and changing course every 2 seconds. More than 23 and changing course, in all these cases, the reporting interval is every 2 seconds. So you see, as the faster the ship moves, faster the data changes, the faster frequency has been allotted so that the data displayed by the AIS is up to date and correct. Let us now go into the 3 different modes on which the AIS works. The first one of them is known as the autonomous mode or ship-to-ship mode. This is the normal mode of operation of the AIS, and in this particular mode, the AIS selects its own time schedule or time slot, and it defines its own reporting rate or reporting frequency. This reporting rate or reporting frequency depends upon the navigational status of the ship, which we just now saw in the previous slide. And it also depends upon the speed and course on which the ship is moving, whether the speed and course are steady or they are changing. And in this mode, data is transferred between ships in the VHF range. The second mode under which the AIS can operate is known as the assigned mode. In the assigned mode, a competent authority which is responsible for traffic monitoring, it could be a VTS station or a VTMS station. The VTS or VTMS station may remotely control the operation of the AIS. In assigned mode, the transmission frequency, the slot selection, both of these items are controlled by the VTS only. The assigned mode or the mode under which you are operating under a VTS happens in areas, say, let's something like Singapore Straits or other VTS which you come across. Now, it is possible that the AIS operation may be entirely controlled by the VTS. Now, coming to the third mode, that is the polled or controlled mode. In this mode, the AIS will automatically respond to interrogation messages from a ship or a competent authority like a naval ship. The response is transmitted on the same channel where the interrogation message was received. Operation in the polled mode or controlled mode does not conflict with the operation in other 2 modes. Now, what does this mean? This basically means that if there is a competent authority which wants to capture the AIS data of a ship, it could be a shore station, like at many places you have military naval stations which collect the data. Like, say, for example, India, at our southernmost tip at Indira Point, we have a station which captures the data of the ships which are moving in that area. So they do not have to get the data from the normal mode of operation. If they want, they can actively poll or control the AIS of a ship. Now, what they do is they send a target message. Now, when that message is received by the ship's AIS, it responds to that message, and whatever information has been asked, it supplies that information to that particular station. It could be a naval base, a shore station, or it could be a naval ship which is collecting the data. Now in this mode, the message text also can be edited by the station requesting the data. They may not want all the data of a ship, they may only want some selected items. So in that polling message, this information is also contained and the ship responds to it accordingly. Now, this operation is independent of the other two modes. A ship may be working in autonomous mode and at the same time the polling command is received. So it will keep on working in the autonomous mode without any interference. Now, as per IMO, there are three basic functions which the AIS fulfills. Number one, AIS is considered to be an excellent VTS tool for traffic management. Number two, looking at the security aspect, AIS is considered as a surveillance tool by coastal states, which is used for monitoring the vessels entering or transiting their waters. And AIS is certainly a navigational aid for collision avoidance. So these are the three basic functions of the AIS as listed down by the IMO. Now moving on to another new concept coming in, that is a pseudo AIS. What is this pseudo AIS? Now if we have a VTS and the VTS is having radar as well as a AIS receiver, the VTS center may send information about vessels which are not carrying AIS and which are tracked only by VTS radar via the AIS to vessels equipped with AIS. Now what does that mean? Let us say, for example, you are moving in Singapore Straits. There is a tug and a barge, a tug which is towing a barge trying to cross the traffic lane. Now that tug being smaller is not mandatorily required to be fitted with a AIS. So you will not get that tug on your AIS screen. Now the VTS has a radar station. VTS, the tug reports to the VTS. VTS knows that the tug is going to cross the lane. Now what the VTS can do is, they are picking up that tug on their radar. The ARPA is giving them the required data. What is the course, what is the speed, everything. What the VTS can do is, they can transmit this radar and ARPA information about that particular tug through the AIS frequency. So what will happen on your AIS screen? You will start to receive the data of that particular target. So even though the tug was not having any AIS equipment on board, other ships will still be able to see it on their AIS. Now that is known as a pseudo AIS. Now the requirement is that any pseudo AIS target broadcast by the VTS should be clearly identified as such. So there are some specific symbols which may be used by the VTS to show a pseudo target. There is a IMO resolution also which tells us what symbols should be used in the AIS. Particular care should always be taken when using information which has been relayed by a third party, because there is a scope of error or erroneous information creeping in. The accuracy of these targets may not be as accurate as the actual directly received targets by the AIS system. And the information content may also not be complete. Now moving on to the third usage of AIS, AIS as an aid to collision avoidance. AIS has the potential to significantly contribute to safety of navigation. It provides positive ID, positive identification of targets, along with their static and dynamic data, which helps a lot in decision making by the OW in ROR situations. It can greatly improve the situational awareness of the OW. It also assists in tracking and monitoring targets as it provides information on CPA and TCPA. Going further in collision avoidance, AIS is a very useful tools for positive identification and helps in collision avoidance. But when we are using AIS in the ship-to-ship mode for anti-collision purpose, we should be using some precautions. It should always be kept in mind that AIS is an additional source for navigational information. AIS does not replace but supports the navigational systems such as radar, target tracking, and VTS. The use of AIS does not negate the responsibility of the OW to comply at all times with the collision regulations. So another important thing which you will see here is that AIS is not that much widely mentioned in the collision regulations as compared to the radar. There are some rules which are very much specific to radar. So it tells us that the weightage which is given by the call regs to the equipment is much more to the radar as compared to the AIS. So basically it is for this purpose which I discussed a little bit before, that AIS is a GIGO system, garbage in, garbage out. That means there is no way to check the authenticity of the information. If the AIS shows you a target at a particular place, it is very much possible that there may be no target and the target may have moved to some other location. But radar will only show you a target at that particular place if it is actually there. Barring a few limitations of the radar is much more reliable as compared to the AIS. So AIS is an additional source and it cannot replace the existing navigational systems. User should not rely on the AIS as the sole information system and should make use of all safety relevant information available from other sources also. So coming to call regs once again, rule 5 in call regs says every vessel shall at all times maintain a proper lookout by sight and hearing, and as well as by all available means. Now this is what we need to highlight here, all available means. AIS certainly makes a part of these all available means. Even though it is not specifically mentioned in call regs to be used, but these all available means give us a lead to utilizing the AIS information. So in the light of features offered by AIS and its advantages, it certainly forms an integral part of the available means for making full appraisal of the situation. Thus, it is not only desirable, but also imperative on part of the OW to utilize AIS and enhance his or her situational awareness. Okay, beta. So that brings us to the end of AIS. Now, any doubts coming in the AIS equipment, beta? Clear? AIS is clear? Okay, all right, beta. Yes, great. Sir. Very good. So now, beta, next equipment Shall we pick up the autopilot? We have basically the autopilot, the VDR, and the Banvas. So shall we pick up the autopilot for now?
Okay.
Okay, all right. So let's go to autopilot. In this presentation, we are going to discuss and learn about the autopilot, the ship's heading control system. Now, before we go into the SOLAS requirement concerning the autopilot, let's have a look at what is a track control system. A track control system is designed to keep a vessel on a predetermined track throughout its passage and must be interfaced with the GPS or an ACDIS to carry out this function. The track control systems are much more advanced and complicated as compared to a autopilot, which is a heading control system. The track control system have all the capabilities of heading control and on top of it maintain the vessel within a particular track. If you feed a particular track of the ship using waypoints, and if you feed a certain value of the cross track error which is acceptable, the track control system will automatically give the set if required and maintain the ship within those parameters. Now, for doing this function, it needs to have a GPS feedback or a ACDIS feedback where the positioning is being done regularly, and it knows what is the set is to be given to keep the vessel in the desired track. Autopilot is much simpler as compared to a track control system. Autopilot is called as a heading control system. It does not monitor the track of the ship. What it monitors is the heading on which the ship is moving. Moving on to the SOLAS requirements concerning the autopilot. The SOLAS Chapter 5, which is the Safety of Navigation, Regulation 19. This regulation is concerning the bridge equipment present on board a ship. It says that all vessels of 10,000 gross tons and above must have a heading or track control system, but the track control is not mandatory. So as we just now discussed in the previous slide, the autopilot is a heading control system. Also, this regulation says that masters and navigating officers must be fully conversant with the operation of the autopilot and especially the changeover procedures from auto to manual and manual to auto. Let's now move on to the working and the controls present on a autopilot, the concept on which it works. A basic autopilot is also called as a PID autopilot. PID stands for proportional, integral, and derivative control. So we will now see one by one what do all these controls mean and how does the autopilot functions under the effect of these controls. Let's first go into the first control, which is known as the proportional control. The proportional control is basically the rudder control. Now, with this form of control, the rudder is moved by an amount which is proportional to the off-course error. That is the difference between the gyro heading and the set course. So whatever is the difference between the gyro heading and the set course, proportional to it, a command is given to the rudder, and the rudder tries to bring this difference to 0. So whenever the heading of the vessel goes haywire from the set heading, immediately the proportional control detects this difference and the rudder moves by an amount in the opposite direction which is proportional to this difference and brings the heading of the ship back to the set heading. Now this proportional control also has a downside. What is the downside with the proportional control? You see, as the vessel returns back towards the set course, she is going to overshoot the required heading due to inertia and will now start to apply the corrective helm in the opposite direction. This process keeps on repeating itself and leads to an oscillation of the ship's track about the required heading or the required course. And this results in increased steaming distance, a zigzag kind of track being followed by the ship, increased rudder drag, and increased wear and tear of the steering gear and the rudder components. So this is checked by the next control which we are going to see, that is called as a counter rudder control. You can easily understand it from this diagram. Let us say at this particular instant, the vessel's heading had gone off from the set heading. Now you see there is a differential, there is a difference between the set heading and the actual heading, and a rudder angle is given, a rudder order is given. Since the vessel has swung to the port side, the helm order will be given as a starboard helm. Because of this starboard helm, the vessel starts to bring back the heading to the set heading, and till the time the vessel attains the set heading, the rudder order will remain to starboard only. Now when the vessel reaches on the set heading, at that time the difference between the set heading and the actual heading of the ship is 0 and the rudder will come back to 0. But you see the vessel has already attained some rate of turn and there is a swing of the ship to starboard. Now because of this swing, the vessel is now, the heading is now going to overshoot to the starboard side, and you will see the vessel swinging on to the starboard direction. So once the vessel swings to starboard, again a differential is generated, a difference is generated between the actual heading and the set heading. This gives a port helm order to the rudder. The rudder sets on a some port helm value, and this starboard swing of the ship is checked, and after a certain time you will see the starboard swing of the vessel is entirely checked and it again regains the set heading. But by the time it regains the set heading, the rudder angle now becomes 0. But again the vessel has gained some rate of turn, this time toward the port side, and it is going to overshoot to the port side. So because of this overshooting, the vessel moves on a zigzag kind of track, leading to more wear and tear, leading to a non-effective sailing, leading to more rudder drag, lesser fuel efficiency, and more time taking. So this is a downside of the proportional control, which we will be checking with the derivative control. Now related to the proportional control, there are basically two settings which are provided in the autopilot. One is the rudder setting. The rudder setting basically tells us how sensitive should the rudder be to the proportional control. A lesser rudder order should be given or a higher rudder order should be given. That is what is decided by the rudder control. And a second setting which is related to the proportional control is the maximum rudder angle or the rudder limit. So once this rudder limit is input by the navigator, whatever the proportional control orders, the rudder will not cross that particular limit. Now moving on to the derivative control, the second control. With this form of control, the rudder is moved by an amount which is proportional to the rate of change of the ship's heading, or in short, the rate of turn. So the basic idea behind the derivative control is to kill any rate of turn generated because of the swinging of the ship. Now this assists and supports the proportional control which we saw earlier. So let us try to understand it using this diagram. Let us say at this particular point, the vessel has swung to port side and has gone off course. The set course is represented by the dotted line. The vessel has gone off course now, and you can see the vessel must be swinging to the port side to go off course. Now when the vessel is swinging to the port side, a certain rate of turn is generated, and this derivative control tries to kill that rate of turn. So the derivative control will give a order to the rudder to swing, to have a rudder angle to the starboard side, so that this port side swing can be checked. Now at a certain point of time, you will see the heading will be stationary, will stabilize. Let us say the heading has stabilized in the direction of the arrow. Now as soon as the heading is stabilized, the rate of turn becomes 0. Now after this, the proportional control will still be ordering a starboard rudder, a starboard helm, because it wants to bring the heading of the ship to the desired heading, to the set heading. So what will happen after this point is, under the effect of the proportional control, the vessel will start to swing to starboard now. As the vessel starts to swing to starboard, a starboard rate of turn is generated, and now the derivative control tries to kill this starboard rate of turn and gives a order of the port helm. So this derivative control is basically trying to counter the rudder control now. And what is the benefit? What is the advantage? The advantage is that as the vessel comes back to its original set heading, so you see at this particular point represented by X, the vessel is now heading in the set direction. So the proportional control will become 0. There will be no rudder angle because of the proportional control, and the derivative control will now stop the vessel overshooting to the starboard side. Because the derivative control is continuously trying to kill the rate of turn. So from this point here where the laser pointer is to point X where the vessel has regained its heading, it was swinging to starboard, and the derivative control was giving a port helm to check this swing. And when the vessel reaches here, because of this derivative control or the counter rudder control, there is no overshoot to the starboard side. Thus the overshoot is avoided, and the vessel starts to move on a track which is same as the set heading or the desired heading. So you see, a combination of the proportional control and the derivative control makes the control of the heading very smooth process. With only proportional control in action, the vessel was overshooting to starboard and to port and was moving on a zigzag kind of track. But with the derivative control, now the rate of turn of the ship being checked, the vessel very smoothly comes on the initial heading and then continues to move on it. Now moving on to the third control which we have, that is called as the integral control. This integral control is nothing but basically a automatic permanent helm. We know there is a permanent helm setting which is provided in the autopilot. So this integral control is nothing but a automatic version of that permanent helm. Now the data for this integral control is derived by electronically integrating the heading error. Basically what the system does is it continuously senses what is the heading error being generated. Once you have gathered the heading error being generated, you can easily identify if there is a permanent force trying to take the ship off course continuously and regularly. Let us say, for example, if you have a beam wind or a counter current, or the vessel is listed to one particular side. Now, because of all these reasons, there will be tendency of the ship to swing to one particular direction. So this integral control basically senses this tendency of the ship and applies a permanent helm automatically. So the action of this data which is collected is to offset the effect of vessel being moved continuously off course due to a effect of wind, current, or a certain list condition or trim condition or a certain hull form, etc. The data signals which are produced continuously sensing the heading error over a period of time are picked up, and they are used to apply an appropriate degree of the permanent helm. So as I told you, a manual setting of the permanent helm is also available to us, and it can be manually used by the duty officer. But if it is not utilized, the integral control will do the same job automatically. So you can understand the concept of this integral control from this diagram very easily. We have the dashed line representing the course to be steered by the ship. Now let's say there is a continuous sideways force which is affecting our ship. You can say there is a wind coming from the starboard beam or a counter current coming from the starboard beam, pushing the ships towards port. Now the proportional and derivative control will try to maintain the heading of the ship, but they get activated only when the vessel goes off track. Either there is a change in the actual heading of the ship from the set heading, or a certain rate of turn is generated. Only then the proportional and derivative control come into action, and they try to bring the vessel back to the original track. So as a result of which, you will see the vessel will continue to be pushed in a lee direction, the direction in which the wind or current is pushing us. But with this integral control, what happens is the integral control senses this motion of the ship and applies a permanent helm continuously. So with this permanent helm, the vessel is not pushed to the leeward. What happens is the vessel maintains the course to steer, and a very less, or you can say the cross-track error is minimized to a great extent. The proportional and derivative control are not able to minimize the cross-track error, but the integral control successfully tries to minimize the cross-track error as much as possible, because once it has sensed this permanent force acting on the ship's hull, pushing it sideways, it generates a permanent helm and kills this force in the first hand. It does not wait for the ship to go off track or to generate a rate of turn. What it does is continuously keeps on altering or counteracting that force, keeping the vessel on the desired track. So with all these three controls in action, that is the proportional control, the derivative control, and the integral control, the track of the ship now looks something like this. At this particular point, the vessel has gone off heading. So you can see the proportional control and the derivative control coming into action, bringing the vessel back here. There is a slight overshoot. So vessel goes on to the starboard side of the track. Again, it comes back. It is brought back by the P and D controls. The integral control is gathering information all this while. Again, there is a slight overshoot and the vessel reaches up to this particular point. And here onwards, the integral control also kicks in, giving a permanent helm, counteracting this continuous force which is trying to disturb our set course, the actual course. So after this, the vessel moves nearly on the set track, on the set heading, without any deviations. So you see the deviations being smoothened up by the action of the PID and the vessel following its intended track. Now, having understood the PID controls of the autopilot, let's try to understand the complete autopilot working using this block diagram. Now, this looks very complicated in the beginning, but once you understand it step by step, everything starts to become clear. So we see this blue shaded portion is known as the control unit. Now, in this control unit, there are two feedbacks which are going. One is the actual heading of the ship from the gyro compass, and the second is the set course, the course which is set by the navigator. Now, with these two feedback coming, it first goes into a course comparator. It basically compares both these things, that is the actual heading of the ship as well as the set course, find out the difference between them, and basis that gives the command for rudder. Now this command further passes from the differentiator or differential control, which is basically the counter rudder. The counter rudder comes into action whenever the vessel swings. Whenever the vessel swings and some rate of turn is generated, it tries to kill that rate of turn and bring the rate of turn to zero again. A input is also obtained from the integrated or integral control, which is basically a automatic permanent helm. So this continuously keeps on judging the external factors, external forces acting on the ship, trying to continuously alter the course in one particular direction, and gives a permanent helm to counteract that continuous force. All these three inputs, that is the input from course comparison, input from the integral control, and the input from the differential or counter rudder control, are summed up or are added up in this summing amplifier. The summing amplifier adds up these three feedbacks and passes them on to what we call as the error amplifier. Now, what is this error amplifier? Error amplifier receives a command which is to be given to the rudder from the summing amplifier, and this error amplifier also gets a feedback from the rudder that what is the present position of the rudder. So this error amplifier comes to know that this is where the rudder is supposed to go and this is where the rudder is right now. Basis these two, it sends further feedback or instruction to the steering gear compartment. Now this instruction passes from the rudder limit. If the order exceeds the rudder limit which is set by the navigator, then in that case the rudder order is limited to the set value. Once this is limited, it passes on to the telemotor transmitter. This basically converts it into a digital signal, and it is passed on through wires to the steering gear compartment. In the steering gear compartment, we have a telemotor receiver. The telemotor receiver receives this digital signal and converts it into a command which is given to the steering gear and the rudder. The steering gear comes into operation. The rudder moves on to the desired indication. This is sent to the rudder feedback module, which gives the current position of the rudder, the actual position of the rudder, to the rudder angle indicator in the bridge, as well as to the error amplifier. So once this feedback goes to the error amplifier, it comes to know that whatever order was given by the summing amplifier and the actual position of the rudder are now matching. So it stops sending any further signals and the rudder stays in that particular location. When the vessel has attained the desired heading and there is no rudder angle required, the summing amplifier sends a zero command to the error amplifier. The error amplifier checks this zero command against the actual position of the rudder, gives a command further to the rudder, and the rudder comes back to the zero rudder angle position. Now, all the controls which you see here with the circles on them, like you see this control, which is the set course control. This is a feedback input by the navigator into the system. The course is set by the navigator. The second feedback which you see is the off course alarm. So this off course alarm is also fed in the what should be the value at which the off course alarm should be given. That is fed into the system. And whenever the course comparator finds that the actual difference between the set course and the actual heading of the ship is more than the off course alarm level, it starts to give an alarm alerting the navigator. Then the differentiator or the counter rudder, this can be controlled, the value can be controlled. Then further you see this is the rudder rate. It is basically the rudder control. That means proportional to the difference between the set course and the gyro course, what command should be given to the rudder. This is set by the rudder rate feedback or control, which is set by the navigator. Then we have a permanent helm. This is basically a manual input. In case the navigator finds the ship steering in one particular direction, swinging too often time and again in one particular direction, he can set up a permanent helm value which gets into the system at this point, and then it is fed into the error amplifier. Then we have the yaw or weather control feedback. In case of bad weather, there will be very frequent deviations from the set course. And if the rudder keeps on trying to correct those deviations, the steering gear will be overused. So to avoid that scenario from happening, what is done is when the weather becomes bad, this yaw or weather control setting is increased. So what it does is it generates a dead zone. That means up to a particular deviation, no rudder order will be given. Only when the vessel's heading goes out of that dead zone, it crosses a certain value to starboard or to port, only then the order will be given to the rudder and the rudder will move. So this prevents the overuse and overheating of the steering gear as well as the rudder. Then we have the rudder limit setting. This is the maximum amount of rudder which can be given in a particular condition. So this is set by the navigator, and whenever an order is given to the steering gear or the rudder, it passes from this rudder limit module, and in case the order is more than the set rudder limit, the order is brought down to the set limit and then forwarded to the steering gear compartment. So beta, have a good look at the block diagram. Let me know any doubts coming in this. This is by far the most important question in autopilot. Most of the time you will see explain the working of the autopilot using a block diagram. Question like this coming in your exams. Clear beta? Understood? Go ahead beta.
So this off course alarm, so like for example, we have set the off course alarm to 5 degrees and we have set the course to 10 degrees port or starboard. So exactly when this off course alarm gets activated?
Beta, if you have,
yes.
yeah, if you have set the off course alarm at 5 degrees, whenever the gyro heading goes more than 5 degrees from the set course, that is the time when it will give you the off course alarm.
Right, sir. Okay.
Okay.
I'm asking, sir, like while we are making any alterations, now normally we get, if there is a choppy weather, we keep getting this off course alarm on the bridge. So I'm asking, like, suppose if you have set the course to 10 degrees starboard or port, but the off course alarm is 5 degree. So exactly when it's supposed to give the alarm, when you're altering or something like that.
Okay. Now, if you are altering the course beta, let us say the vessel is steering 000 and your next course is 030. Okay. So अब आपने जो है वो set course वहां पे 030 डाल दिया. Now,
Yes,
till
sir.
the time the difference between the actual heading and the set course is more than 5 degrees, the off course alarm should keep on coming.
So means suppose we have off course alarm of 5 degree and we are giving set course like 10 or 15 degrees to the starboard. So you mean to
Right.
say that off course alarm should get activated until that
Yes, it should. It should. Let us say आपने 030 course
5
set
degree
कर
gap
दिया.
is reached.
या आपने 030 कोर्स सेट कर दिया. अभी एक्चुअल हेडिंग है 000 एंड जैसे ही आपने सेट किया इमीडिएटली यू विल गेट दिस ऑफ कोर्स अलार्म. अगर तो आप इसे रीसेट कर देते हो तो ये बंद हो जाएगा. बट अगर आप इसे बजने देते हो तो ये कब तक बजता रहेगा. वेसल इज स्विंगिंग टू स्टारबोर्ड. आफ्टर सम टाइम इट विल कम टू 010 020. एज सून एज इट कम्स टू 025 and it is within 5 degrees of the set course, then is the off course alarm, the point where the off course alarm will get off.
Okay, sir. Okay, sir.
Okay, beta.
Thank you, sir.
Okay, all right. Great, beta. So let's take a break here. इसके बाद एक टॉपिक हमारा बाकी है ऑटो पायलट में, दैट इज नोन एज ऑटो अडेप्टिव स्टीयरिंग और ऑटो अडेप्टिव ऑटो पायलट. वन इंटरेस्टिंग थिंग अबाउट ऑटो पायलट, अभी हमने ये पीआईडी ऑटो पायलट देखा बेटा. यू हैव सीन अभी एलन मस्क स्पेस एक्स में दे हैव लॉन्च्ड ए रॉकेट एंड वो जो बूस्टर था दे हैव कॉट दैट बूस्टर बैक. ओके, सो दे आर यू अवेयर ऑफ दिस? एनीबडी गोइंग थ्रू द न्यूज़?
Yes, sir. We saw.
राइट, देयर वाज ए नाइस वीडियो आल्सो जिसमें उन्होंने उसको वापस कैच कर लिया अपने स्टैंड पे. पहले ये ओशन में एक्चुअली एक प्लेटफॉर्म पे इसे रिट्रीव कर रहे थे एंड नाउ दे हैव कॉट इट बैक इन दैट सेम स्टैंड. सो दैट इज आल्सो यूजिंग a PID autopilot. So that PID autopilot brings that rocket back. Okay, after removing the payload, the rocket booster is brought back using that PID autopilot only. Okay, great. गुड बेटा. सो लेट्स टेक ए शॉर्ट ब्रेक. ब्रेक के बाद हम लोग ये ऑटो अडेप्टिव स्टीयरिंग देखते हैं. ऑटो अडेप्टिव स्टीयरिंग इज नथिंग बट इट्स लाइक आर्टिफिशियल इंटेलिजेंस. आजकल एआई बहुत चल रहा है ना. सो एनीथिंग यू वांट टू आस्क द एआई विल आंसर इट फॉर यू. सो द सेम एआई, artificial intelligence, has been present long time in our autopilot, and this auto adaptive steering is nothing but that artificial intelligence. So we will see that after the break. So let's be back after 5 minutes, beta. कि बेटा चलें आगे, बैक। आगे वापस।
Yes, sir.
Okay, all right. Let's go, beta. Let's see the auto adaptive steering or auto adaptive autopilot. Let's now go into auto adaptive steering system. Most of the modern autopilots, they have a capability to automatically adapt to the prevailing circumstances and order an effective steering of the ship, which is known as a auto adaptive steering. The auto adaptive steering system is an advanced version of the conventional autopilot, which adapts to the steering capability of the ship as well as the weather conditions. So basically there are two inputs to the auto adaptive steering system. One is the steering capability of the ship and second is the present weather condition. Basis both these factors, it automatically adapts the entire steering system and results in very effective steering. Unlike in the case of the PID autopilot, in auto adaptive steering, the optimum steering is achieved without any manual adjustment. Everything is done automatically using sensors and using a reference model of the ship without any manual intervention required from the navigator. So let's try to understand this auto adaptive steering system. We see this block diagram here on the screen. Now in this block diagram, you first see a estimation unit. Now the estimation algorithm is based on what we call as a model reference adaptive control system, in short known as MRACS. You can see this MRACS here in the block diagram. Reference model hull dynamic characteristics. What is this MRACS? It is basically a small software where the model of the ship is fed in. Any forces which are acting on the ship can be judged by this model, and this model predicts the behavior of the ship. So any forces which are acting on the ship are predicted using this reference model, a software model. Now this MRACS gets its input from the gyro speed log and the rate of turn indicator. So it gets to know what is the heading of the ship from the gyro. It gets to know what is the speed with which the ship is moving. And it gets to know what is the rate of turn which the vessel has generated, or in which way is the vessel swinging. Now this MRACS, model reference adaptive control system, or the model of the ship which is present in the software, it gets the information from gyro speed log and rate of turn indicator and passes on this information to the optimal controller. So it basically tells the optimal controller how the ship is behaving in a particular situation. Whatever course is set by the navigator, that set course is also fed into the optimal controller. So the optimal controller now knows what is the set course, what is the gyro heading of the ship, how is the ship behaving in the particular condition, in this particular weather, what is the speed of the ship, what is the swing of the ship, is the ship swinging to starboard or to port. Now this entire information is available to the optimal controller. The optimal controller then calculates the rudder angle which is to be ordered based on the inputs received from the MRACS in comparison with the course which is selected by the OOW. Now we come to another important part of the auto-adaptive steering system, that is the adaptive Kalaman filter. In open sea, vessel is subjected to various disturbances caused due to wind, sea and swells, which result into yawing. In case of the PID autopilot, controls have to be manually adjusted to reduce the effect of the yawing. In the case of the auto-adaptive steering, the adjustment is done automatically by means of a adaptive Kalaman filter. So you can see this adaptive Kalaman filter here in the block diagram. So this Kalaman filter basically gets a feedback about the ship's particulars from the gyro, speed log and rate of turn indicator. It also gets a feedback from the reference model of the ship which we have in the software. And basis these factors, it gives a feedback to the optimal controller. Basically, the integral control or the permanent helm control, which was manually set in a PID autopilot, is now sensed by this Kalaman filter, and accordingly a order is given to the optimal controller to factor this in. It also gets a feedback from the steering gear. How is the steering gear operating? And basis that, it keeps on sending the updated command to the optimal controller for the effective steering of the ship. The same thing is explained here. The Kalaman filter gets the inputs regarding the model of the ship from the MRACS, Model Reference Adaptive Control System. This is basically the software model of the ship. This acts as reference as to how the vessel should be behaving normally in comparison with the present behavior due to yawing. So MRACS tells the Kalaman filter how the vessel should be behaving ideally, and the input from gyro, speed log and rate of turn indicator tells the Kalaman filter how the ship is behaving actually due to the present weather conditions. Now, based on the comparison of the model ship and the present parameters, the Kalaman filter gives the output to the optimal controller. So from the Kalaman filter, getting its feedback from gyro, speed log and ROTI, as well as from the MRACS, it sends a command to the optimal controller, which then gives a command to the steering gear and results in optimum or effective steering of the ship. As the weather conditions change, the yawing is also affected, and the Kalaman filter adapts to these changes automatically, and output from the filter will vary accordingly. Thus, in this entire system, no human intervention is required, and this system automatically keeps the autopilot tuned to the most effective steering in the given scenario, in the given conditions. Okay, beta. All right. So that brings us to the end of the autopilot. Now, any doubts in your mind, beta, in autopilot anywhere? Okay, beta. Great. That's great. Okay. So now after autopilot, beta, we are left with two more equipment. These are the VDR and the Banvas. So which equipment you want to take first?
VDR, sir.
VDR? Okay, great. Let's take the VDR, the voyage data recorder, black box on our ships. Huh? Okay, let's go. Let me put up the presentation. In this presentation, we learn about the voyage data recorder. Now, a voyage data recorder can be very easily understood by going into the performance standards for the voyage data recorder equipment. These performance standards are given by resolution MSC 333-90 and they were adopted on 22nd May 2012. So we will be discussing this equipment through its performance standard. Right now you see the circular, IMO resolution circular, which gives us the performance standards for the VDR equipment. The first part of the resolution gives us the reasons why these performance standards were brought in. Then in the second part, you see that the IMO has adopted the revised recommendation on performance standards for voyage data recorder. Now these standards were updated from July 2002. The first standards were brought in from July 2002 and these standards were revised on 1st July 2014. So we are discussing the standards which are in force after 1st July 2014. So the resolution recommends the governments to ensure that if a VDR is installed on or after 1st July 2014, it should comply with or conform to performance standards not inferior to those specified in the annex to this present resolution. At the same time, they have given a relaxation to the ships where VDR has been installed before July 2014. They can continue to comply with the performance standard which were specified in the earlier resolution A861-20. Now the first part of the resolution tells us about the purpose of the voyage data recorder equipment. The purpose of a VDR is to maintain a store in a secure and retrievable form of information concerning the position, movement, physical status, command and control of a ship over the period leading up to and following an incident having an impact thereon. Information which is contained in a VDR should be made available to both the administration and the ship owner. Basically, the ship owner is the owner of the VDR data and he has an obligation to provide this information to the administration for accident investigation and analysis. This information is for use during any subsequent safety investigations to identify the causes of the incident. Now, if an accident has happened, the only way to learn about that accident and to prevent it from repeating again is to learn from our mistakes. And this is exactly the purpose of a voyage data recorder, so that we can analyze the reasons, the causes which led into a particular accident, and later on we can eliminate them to make shipping more safer. We come to the definitions now. Voyage data recorder or VDR means a complete system including any items required to interface with the sources of input signals, the processing of the input signals and encoding whatever is required, the final recording medium, also known as FRM, the playback equipment, which is used to play back the VDR data, the power supply, and the dedicated reserve power source. So all these are the parts of a voyage data recorder. A signal source means any sensor or device external to the VDR to which the VDR is connected and from which it obtains signals and data to be recorded. The final recording medium means the items of hardware on which the data is recorded, such that access to any one of them would enable the data to be recovered and played back by use of a suitable equipment. The combination of a fixed recording medium and float-free recording medium and long-term recording medium together is recognized as the final recording medium. So final recording medium basically consists of three parts. First one is the fixed recording medium, which is fixed with the ship, and in case of a unfortunate happening with the ship sinking, this fixed recording medium goes down with the ship. The second part of the final recording medium is a float-free recording medium. It is fitted with a HRU, and in the unfortunate event of a ship sinking, this will float free and remain on the surface. And the third one is a long-term recording medium. Long-term recording medium is just like a computer which is present on the ship, and it records the data for the longest duration possible. Now moving further to the very important standard about the continuity of operation of the VDR. Now in normal operation, the VDR should be working from the ship's main power supply, and in case because of any reason the ship's main power supply fails, it should automatically change over to the emergency source of electrical power. Now in case the electrical power emergency supply also fails, then the VDR should continue to record the bridge audio from a dedicated reserve power source for a period of 2 hours. At the end of this 2-hour period, all recording should cease automatically. So in case the ship's main power supply and the emergency power supply fails, the VDR should have a dedicated reserve power source. It is a battery which is basically independent of all the other power sources or equipment, and it is dedicated solely for the voyage data recorder. And this battery enables the VDR to record the bridge audio. See, when there is a main and emergency power supply failure, all the other bridge equipment will automatically be shut down, so there will be no recording in the VDR also. But the VDR should keep on recording the bridge audio. Now the purpose behind giving this dedicated reserve power source is that if there is an incident and the ship's main power supply and after that the emergency power supply has also stopped or it has been exhausted, it is still possible that activities may be going on the bridge. And to capture those activities, the bridge audio should remain on. So a period of 2 hours has been dedicated, and at the end of this 2-hour period, all recording should cease automatically. So this is one important standard which 5.4 tells us. The second important point, very, very important standard, which tells us about the duration of the data recorded is the time for which all stored data items are retained should be at least 30 days or 720 hours on the long-term recording medium. So you see we have three parts of the recording medium. These are the long-term recording medium, float-free recording medium, and the fixed recording medium. So for these three, the duration of recording is also different. For the long-term recording medium, we should have a recording of the last 30 days or 720 hours. And for the fixed recording medium and the float-free recording medium, For both of them, the recording duration is 48 hours. The data items which are older than this duration may be overwritten with the new data. Now moving on next to the most important standard in the voyage data recorder, that is the data items to be recorded. This basically forms the core of the VDR. Now the first and very important data items which is recorded is the date and time. The date and time reference to the UTC or the GMT should be obtained from a source external to the ship. Now this, for example, could be the GPS time. This GPS time is derived from the global positioning system, and it is something which is external to the ship. This time is not generated on the ship, but generated from the GPS system. Now, in addition to this, there should be an internal clock. This internal clock should be automatically synchronized with valid date and time data. Now, why do we have an internal clock? This is given as a backup. During times of a loss of the external source, in case of a GPS failure, the internal clock time should be used by the voyage data recorder. The recording should indicate which source is in use. So at any time when the VDR recording is being checked, it should be able to find out which of the data source for date and time was being used. Moving on to the next data items, that is the ship's position. The latitude and longitude and also the datum used should be derived from an electronic position fixing system, EPFS. This is also a system, a satellite navigation system like GPS, or in some other case it could be the GLONASS or the Galileo. The recording should ensure that the identity and the status of the EPFS can always be determined on playback. If the ship is having two GPSs, then the identity from where the GPS position is being picked up should also be recorded. And if there are any alarms and indication in the GPS, which means related to the status of the equipment or status of the position, that also should be picked up by the or recorded in the VDR. The next data item which is recorded in the VDR is the speed of the ship. The speed of the ship is provided to us by the log. We could have a Doppler log or an electromagnetic log. It is also known as a speed and distance measuring equipment, in short SDME. Now these logs could give us the speed through the water, and they could also give us the speed over the ground. When the ship is in shallow waters, they may change over to speed over the ground. The VDR recording should be such that whatever speed is being given, whether it is speed through the water and whether it is speed over the ground, it should be recorded in the VDR. Also, it should be included in the recording, or there should be an indication of which speed is being recorded, derived from the ship's speed and distance measuring equipment, which is the log. The next data item is the heading of the ship. Heading as indicated by the ship's heading source, which is basically the gyro compass. The next data item which we have is the bridge audio. Now on the bridge, we should have microphones which are positioned on the bridge covering all the workstations, and as described in this MSc circular 982, so that the conversation is recorded. This circular basically explains in detail how these microphones should be positioned on the bridge so that all important conversation is properly recorded. The recording should be such that on playback, a normal speaking voice should provide adequate intelligibility. The sensitivity of the microphones and the location of the microphones should be maintained in such a way that a normal speaking voice in the bridge area should be recorded with intelligibility, means the person listening to that recording should be able to make out what was being said while the ship is performing its normal operations. This performance should be maintained at all workstations, so sufficient number of mics should be fitted so that all workstations, whether it is the helmsman or the coning position or the lookout man, whenever they are speaking something, it should be intelligibly captured. Now, the recording should be intelligible even when there is a single audio alarm anywhere on the bridge. Even if there is any noise, including noise from any faulty equipment or noise from any mountings or from the wind, even with those noises, the microphone should be able to capture the sound. Now, to help in intelligibly hearing or getting what was being said, they have given a provision that this bridge audio should be recorded on at least 2 separate channels of audio recording. Now it basically means 2 separate channels basically means that let us say there is a helmsman and the master. The master has given an order from a different mic and the helmsman is repeating that order and it is being captured from a different mic. Now when you are listening to that recording, since they are on different channels, these voices are not mixed together. You can switch off any of the mics and listen to what the other person was saying. And later on, you can switch on the other mic and listen to what the helmsman was saying. So these voices will not get mixed up. These voices will remain separate and they can be listened to one by one, making the whole picture clear what was happening on the bridge. What was the order given by the master? What was the order repeated by the helmsman and what was actually happening on the bridge? All these things will be recorded. Now microphones which are positioned outside on the bridge wings should be recorded on at least one additional separate channel. Now this is because on the bridge wings there could be various other noise sources which could lead to disturbances, leading to disturbance in the voice, reducing the standard or quality of the recording. So for this reasons, the microphones which are positioned outside are recorded on a separate channel. These can also be switched off during any playback of the recording so that the internal recording can be intelligibly picked up and captured. The next item which we have is the communications audio. We had seen the bridge audio. Now this is the communications audio. The bridge audio basically captured the internal communication on the ship between the master and the helmsman, the duty officer, the lookout man. The communications audio basically captures the communication outside the ship with third parties. So VHF communication relating to the ship operation should be recorded and it should be recorded on an additional separate channel, which means that you should be able to hear this particular channel independent of all the other audio recordings. Next item which we have for recording is the radar information. So the electronic signals of the main displays of both the ship's radar installations should be captured, picked up by the VDR. Now the important thing is that the recording method should be such that on playback, it is possible to present a faithful replica of the entire radar display that was on view at the time of recording. What that means is that whatever radar picture was visible to the duty officer, the same radar picture is recorded in the VDR. Now, if the duty officer increases the range or reduces the range, that is also evident in the VDR recordings. And if he is doing anything on the radar, like he puts on the range rings or he puts on the VRM or the EBL, he takes a bearing, all the actions which he is doing on the radar screen, these actions are captured in the radar recordings. The next item is the EGDIS recording. So when a vessel is fitted with a ECDIS, the VDR should record the ECDIS display, which is in use at the time as the primary means of navigation. And what was applicable in case of radar is also applicable in case of ECDIS, that the recording method should be such that on playback it is possible to present a faithful replica of the entire ECDIS display that was on view at the time of recording. So whatever view was available to the duty officer, whatever scale or range he had selected on the ECDIS equipment, whatever items he was using, a EBL or a VRM or a position line or a range and bearing, whatever was being done practically on the ECDIS screen, that should also be captured in the VDR recording. So basically the person who is watching the recording should be able to see or should be able to check what was the duty officer or the operator of the ECDIS doing at the particular time. The next data item which is recorded is the depth information. The depth information is obtained from the echo sounder. This depth information should include not only the depth under keel, but also the depth scale which is being used by the watchkeeper. Also, along with these, any other alarms and indication which is known as status information should also be recorded in the voyage data recorder. The next item which we have are the alarms coming on the bridge. Now the SOLAS requires some minimum alarm information which should be obtainable or available on the bridge. This should include the status of all mandatory alarms on the bridge. So all these alarms, as and when they are coming, it should be recorded in the voyage data recorder. Now a new equipment which is coming on the ships is the BAMS, that is the Bridge Alert Management System. And in case that is fitted on a ship, then the BAMS system alarms should be recorded in the VDR. However, whenever an alarm is recorded in the VDR, it should be recorded as an individually identified alarm. So when you are going through the recording, it should not only indicate you that there was some alarm coming on the bridge, it should also specify what was that specific particular alarm which came at that particular time. Now you can see a BAMS system with a very simple block diagram. You can see this BAMS system is connected with all the bridge equipment, and any alarms coming in these equipment are passed on to the BAMS through digital communication or serial communications. And you can acknowledge these alarms from the BAMS itself, and these get acknowledged in the individual systems also. Also, you can see the BAMS communicating with the voyage data recorder. So this entire information which is coming in the BAMS system is captured or recorded in the VDR. The BAMS is connected to a buzzer also, which sounds whenever there is an alarm. The duty officer can come to the BAMS, see the status of the alarm, can acknowledge it from here, and then later on can go to that particular equipment to see the specific indication given by that alarm. The BAMS system may also be connected with the bridge navigational watch alarm system. The next data item which is recorded is the rudder order and response. Now it is important to note that the rudder order is recorded as well as the response received from the steering system, that is also recorded individually and separately. So a person analyzing the VDR recording should be able to see what was the rudder order given and what was the response received and after how much time the response was received. Also, along with all this information, The VDR recording should also include the status and setting of the heading or track controller, which is basically the autopilot. And the recording should also indicate what is the control station in use. Now on the bridge, you could have different locations where a rudder order could be given. You could have control stations on the bridge wings also. So the VDR recording should indicate which control station was used. What was the mode on which the autopilot was working, whether it was follow-up or non-follow-up, and what was the power unit in use in the steering system. The next item which we have is the engine and thruster order as well as response. Now you can see both these items are recorded. What was the order given on the engines or the order given on the thrusters? And what was the response received? Both these items, the time taken for the response to come, everything can be checked from the VDR recording. The information should include the positions of any engine telegraphs or direct engine or propeller controls and any feedback indications on the bridge, including ahead or astern indicators, and it should also indicate the control station in use. This should also include any thrusters if fitted and indicate the control station being used to give orders to the thrusters. Now next, if there are any hull openings in the ship, the hull opening status should also be captured by the VDR. This should also include all mandatory status information required to be displayed on the bridge by SOLAS. The next data item to be recorded is the status of watertight and fire doors. All the mandatory status information required to be displayed on the bridge should be recorded and captured in the VDR. The next item are the accelerations and hull stresses. Wherever such a equipment is fitted on board, then all the data captured from this equipment should also be recorded in the VDR. Then the next item is the wind speed and direction. Wherever we have a suitable sensor providing us this data, a suitable anemometer, the wind speed and direction should be captured. And along with the speed and direction, its status, whether it is the true wind direction or the relative wind direction, should also be captured. Then the AIS information, all AIS data should be recorded in the VDR. The next item which is captured is the rolling motion of the ship. Now the rolling motion should be captured from an electronic inclinometer if it is installed on a ship. It is not mandatory as of now. So wherever an electronic inclinometer is installed, the rolling motion of the ship should be captured. And the recording method of the VDR should be such that the rolling motion can be reconstructed during playback. So when somebody is watching the VDR recording, he should be able to reconstruct or see how the ship was rolling, what was the amplitude, what was the frequency, what was the rolling period. All these things should be available through this electronic inclinometer. Now this is a newer addition in the 2014 standards. It was not there in the previous standards. The BAMS is also a newer addition. Another new equipment which is coming up on the bridge is the electronic logbook. So the 2014 standards also mention about the data captured from an electronic logbook. Wherever a ship is fitted with an electronic logbook in accordance with the standards of the organization, the information from this should also be recorded. Now, after the data items, we move on to the next standard, which is about download and playback equipment. Now, this standard was not there in the previous performance standards and has been included in the latest standards. The playback equipment was not mandatory, but now with the new standards, the playback equipment has been made mandatory. So it says the VDR should provide an interface for downloading the stored data and play back the information to an external computer. It should have the capability so that the data can be played back in a external computer. Whatever interface is provided, it should be compatible with an internationally recognized format, such as Ethernet, USB, FireWire, or a equivalent arrangement. It should be possible to perform a download of the recorded data for a user's defined period of time. So all this is to make it convenient for the investigating authorities to download the data and play back it on commercially available off-the-shelf computers so that it can be easily accessed. Now some more requirement related to the playback of the VDR data. The standard says the portable storage device containing the software, the instructions, and any special parts which are not commercial or which are not available off the shelf necessary for the physical connection of the external laptop computer should be stored within the main unit of the VDR. Now, if a manufacturer has a specific part which is not available commercially off the shelf in general, now those specific parts should be provided with the main unit of the VDR so that there is no obstruction to downloading of the data. Also, where a manufacturer is using a non-standard or proprietary formats. So if such formats are used for storing the data in the VDR, the software for converting the stored data into open industry standard, which can be played back on a normal laptop or a normal computer device. Such a software should be available or should be provided on the portable storage device, or it should be resident or there in the Voyage data recorder itself. So you can see all these standards are aimed at making it easier for the analyzing authorities, the investigating authorities to download the data so that it is easily available and accessible. So with this, we close out on the performance standards of the Voyage data recorder. Great, beta. So any doubts in the Voyage data recorder? Very good, beta. Great. So we have completed the VDR. Now the only equipment which is left is the Banvas. So let's do Banvas tomorrow. Okay. So only Banvas's equipment is remaining for tomorrow. So positively for sure we will be covering up or completing the syllabus in tomorrow's class. So Banvas will take at the most about an hour or so. So that's what we will do tomorrow. So completing well in time, beta. You have enough time to now go full ahead in the preparation and prepare for your exam. Preparation ठीक चल रही है?
Going on, sir.
Okay, great, beta. Very good. Okay, all right. So that's all from my side for today, beta. So anything you want to ask or share?
Excuse me, sir.
Go ahead, beta.
सर ये जीपीएस तो ठीक है सर, ये ग्लोनास से भी क्वेश्चंस आते हैं क्या?
बेटा ग्लोनास पे एक सिंपल क्वेश्चन आपको आ सकता है. May I write a short paragraph on GLONASS? Okay, that kind of a question can come, okay, but not a detailed question.
Okay, sir.
अगर आप जो मैंने नोट्स भेजे हैं ना आपको बेटा, जीपीएस के नोट्स अगर देखोगे तो मैंने उस पे ग्लोनास पे और गैलीलियो सिस्टम पे, ये दोनों सिस्टम पे एक एक पैराग्राफ जो है वो आपको दिया है. सो जस्ट रीड दैट. एट द मोस्ट दे कैन आस्क यू दिस. सो if it comes, that would be enough.
Okay, sir.
Right? Okay, all right, beta. Great. So let's call it off for today and I will see you tomorrow. Bye bye.